Okay, so we are now in Unit 5. We will talk about implicit differentiation and related rates in this unit. We're going to start with implicit differentiation, and this is day 1 of notes, and we'll start by saying the difference between explicitly given and implicitly given functions. Okay, so if you are explicitly given, it's basically saying y is already by itself. So if y is already by itself, all you have to do is just derive. Okay, so step 1, if it's not by itself, you would get y alone. Okay, so that you had y is equal to whatever, otherwise f of x is equal to whatever. Okay, step 2 would be actually deriving. Okay, after you take the derivative, you would get f prime of x is equal to your answer, or you get y prime is equal to your answer. Okay, the difference between explicit and implicit is that implicit, look at this right here, you have a lot of y's that you really can't get by yourself, by itself, because of the fact that if you were to GCF out of y, you'd say y squared, let's say y plus 1 minus x squared. No matter what you do altering, you're not really ever going to be able to get the y to say y is equal to. Okay, that doesn't mean that you cannot derive. That's where an implicit differentiation comes into play. You can derive, and your goal at the very end is to get the derivative function by itself. So step 1 on this, it's not going to be to get y alone, it's going to be immediately start deriving the function. Step 2, we're not going to get y by itself, we're going to get f prime of x, otherwise y prime alone, thereafter. Okay. Alright, so let's look at our first example. Our first example is the following: y cubed plus y squared minus x squared is equal to -4. Again, I cannot get this alone, so we're going to differentiate. We're going to differentiate with respect to t. Now, respect to t means it's the variable on the bottom of this dy dx field. By now, you should know f prime of x is the same as writing y prime, which is the same as writing dy dx. Okay, so that you know what this means, follow me with a highlight. It's the derivative of the y function in respect to x. Okay, so that means the function is here, and that's like if I was showing you, here's where the y is at. It's the derivative. Another way that you can write this, it's the derivative of x squared minus 5x plus 7. I'm taking that first example, and it's in respect to x. This is the notation like you would see it in your calculator. You would type that in, and then you would get an answer. Okay? So, again, the top one is the function, and the bottom one here is what it's in respect to as far as differentiating. So, let's go ahead and start looking at what in respect to means. So, in respect to t means that my bottom one will be dt, and the reason why this is blank right here as far as d something dt is that you're going to have different variables. It depends on the variable function that you will put there. For instance, y cubed, it has a chain rule feel to it. I could say y cubed is the same, well, when being differentiated, is going to be 3y squared. This is like chain rule. And then you're going to multiply by the derivative of the cream. So times d something, which is dy, over dt. Okay? The reason why this is chain rule is because you're multiplying by the derivative of the cream. And no longer do we have x's as our input variables. We can have a y as an input variable. So it'll be dy, that's the derivative of y, and it's going to be in respect to t. And that's because of what we were told in the question itself. Okay, so let's go ahead and keep going. So we have 3y squared dy dt plus 2y to the first power times dy dt, and then minus 2x times dx dt. Okay, and then it's equal to 0 because of the fact that it still is a constant, and the derivative constants are 0. So this was dy dt, the derivative of y in respect to t for that one as well. And then we have the derivative of x, a different variable, but we're still in respect to t. Let me go ahead and highlight that t on the bottom with green, showing you that it's immediately what we did, or it's reflecting what we were asked to differentiate in respect to, which is way over here at the very beginning. Okay, so now we'll look at another example. This time we're going to take it in respect to w. So just like we did the other one, we would get 3y squared dy dw plus 2y dy dw minus 2x dx dw, and again is equal to 0. My dw's are because of what I was in respect to. And then my function, y and y, are going to represent this dy differential. And then of course the x will be dx. Okay? So let's finally get to here to see where this dy dx comes from that we've been using this whole time. Okay? So this one will be 3y squared, then it will be dy, not dt, not dw, but dx. Okay? Then it will be plus 2y dy dx minus 2x dx over dx is equal to 0. Now again, I'll highlight it. This is the, oops, let me use the green. This is my in respect to. So all of them are in respect to x. My function here was y's, so dy, again from that chain rule piece, and then x, dx. The one that should be standing out to you right now is this dx over dx. It's just 1, so we don't even need to write it down. We could just say that it's 1 and basically not even write it. So we would say minus 2x is equal to 0. Okay? The goal for implicit differentiation is to see which one you're in respect to, so that you can start eliminating which one am I trying to get by itself. So if we solve for dy dx, because again, our goal when we're implicitly deriving is to get f prime of x alone, or y prime, or dy dx alone. So from here, I have 3 separate monomials. I have this one plus this one minus this one. The dy dx's would stay on the left side, and they would GCF out this dy dx, so that my other terms remaining would be 3y squared plus 2y. And of course, I would move this negative 2x over by adding it to the other side. So that when I have to realize there is multiplication happening right here, so that when I divide both sides by that 3y squared plus 2y, I will finally get dy dx all by itself. So 3y squared plus 2y, this would be the actual derivative function for this equation over here. Okay, never were we given y equals anything alone. That would be the explicit. Okay, we were never given it explicitly, so we had to derive first and then manipulate and get dy dx alone at the very end. So let's do another example. Again, you're not always going to be in respect to x. That's the very first thing that you should try to identify is what am I taking in respect to. The default, if not mentioned, is dx. Okay, that's the default. If I don't say it in a problem and I say, hey, take the derivative, you're to interpret dx. Okay, when we're doing related rates, okay, so related rates, whoops, the default for related rates, we're going to say that the default for there will be the t. So that will be d something over dt. Okay, so again, function-wise, no related rates, you're going to say the derivative of whatever function it is in respect to x. But when we do related rates, then you will use the dt. Okay, so let's do this in respect to x. Do not leave any negative exponents or complex fractions in your answer. The first one would be 2x times dx over dx. That's an understood one. But then we're going to go to this product rule that exists here. It would be plus the first times the derivative of the second. It's not dy dt, it's dy dx because we're in respect to x. Plus the second times the derivative of the first. And again, the derivative of the first is dx over dx. It's an understood one. That I don't have to write this. I could just write times 1 if I wanted to. Keep going and you see minus 2y dy over dx is equal to 0. Again, it's always got that chain rule feel to it. From now, you should see this positive will distribute across these two terms. So nothing really is going to change, so I can go ahead and write it without parentheses. So I'm going to write my dy over dx in front of x. and then plus y minus 2, minus dy over dx 2y. Now, I do this by habit. You do not have to, but it just helps me group things together as far as I will leave this on the left side, leave this on the left side, and I will subtract the 2x and the y over. So minus 2x minus y, GCF out of dy over dx. That's why I write it typically in the front, and then I get x minus 2y. Now, you don't have to write it the way I did. If you want to write it afterwards, like we did up here in this step, you're more than welcome to. Just make sure that you know what you're GCFing out. So that will be divided by x minus 2y. Okay, so my final answer will be dy over dx is equal to negative 2x minus y over x minus 2y. Okay, this is written in terms of, so let me highlight that, in terms of x and y. Because all you see over here on the other side of this equal sign are nothing but x and y's. And yes, you could see a constant. You could see something like plus 8. That's allowable. It's just saying I can't have any other variable other than x and y. Okay, so there would be my answer. Right, oops. Right there. Okay. Do I have negative exponents or complex fractions? No, I do not, so I'm good to go. I can go on to the next one. Again, same thing, we're taking in respect to x. So deriving this side, I get this chain rule piece would be secant squared of x times an understood 1 is equal to 3 plus, here's another product rule right here. So I'll go ahead and put brackets or parentheses, whatever you feel comfortable with. First times the derivative of the second, which is cosine of y dy over dx, plus the second times the derivative of the first. And the derivative of the first, again, so here's my first term right here, is an understood 1 because of the fact that we're in respect to x. So I'll just say times 1. If you don't want to write it, you do not have to. Again, this positive will distribute on both terms. So rewriting it, secant squared x is equal to 3 plus, again, force of habit dy dx, x cosine of y. And then it'll be plus sine of y. And my goal is to get the dy dx by itself. So I can move everything to the left now. I can subtract a 3 and I can subtract a sign. Positive and negatives will show you the separation that exists between the different terms. Okay, so you have 3 terms over here on the right side because the positives and negatives are separating all the terms. So we have secant squared x minus 3 minus sine of y, and it'll be divided by this x cosine of y. That's equal to dy dx. And by now you should be able to do that step and skip a step in order to get straight to the answer, because you know that you're going to move all the other ones over and then divide by whatever this coefficient, if you will, is being multiplied by that dy dx. Now we have to check, is it written in terms of x and y? Well, yes, there aren't any other variables on this entire side other than x and y. Yes, there's a constant here, but that is allowable. I just don't have like w or k or anything like that. Alright, so let's move on. Find the derivative. Do not leave any negative. Again, the same thing. Making sure on the previous one I didn't have any negative or complex fractions. And we have product rule. So it'll be the first times the derivative of the second. So the derivative of the second is negative cosine. Oops, no, not negative. It's going to be a positive cosine of y and then dy over dx. Again, there's my in respect to, not dt yet. So first times the derivative of the second plus the second times the derivative of the first, and that would be a negative sine of x. And I'm going to say right here, it looks like I'm subtracting negative sine of x. So going back to parentheses, first times the derivative of the second plus the second times the derivative of the first. Right here, this parentheses is very important because it lets me know that you're multiplying by this negative, that you're not subtracting it. So make sure that you do have this parentheses or some indication that you are multiplying with that negative sign of x. Okay, so first times the derivative of the second plus the second times the derivative of the first is equal to 0. So I see this dy dx, so this entire monomial here will move to the right side. Well, this adding a, whoops, let me get the highlighter. Adding a positive times a negative, this really is subtracting whatever this is. So when I move it over, I'm going to end up adding whatever this product is right here. So I'm going to go ahead and move it over right now. It'll be a positive sine of x, sine of y, because order doesn't matter with multiplication. And on the left side, it would be dy dx is equal to the cosine of x times the cosine of y. Okay? Now I didn't have to GCF that out, but I know that it's multiplication. So when I divide both sides by the cosine of x, cosine of y, I get dy dx is equal to the sine of x, sine of y, over cosine of x, cosine of y. And those of you who already see it, the more simplified answer would be dy dx is equal to the tangent of x times the tangent of y. Okay? And that's because of the fact of how the sines and the cosines are grouped together there and there. Okay, so no negative powers, no complex fractions. I'm good to go. Let's keep going. I'm given the following equation that I'm going to implicitly derive. And I'm going to first find the dy dx just like I've been doing in terms of x and y. So again, we have the product rule here, so it's first times the derivative of the second. Again, it doesn't say here, or yeah, it does right here, what I'm in respect to, but if it didn't, the default is dx. So first times the derivative of the second plus the second times the derivative of the first, which is an understood 1. Then it'll be plus 3 dy dx minus 10x, an understood 1, is equal to 0. So now I would identify the plus and the minuses that I have so that I could see I have 4 terms. Okay? So the 10x would be added to the other side. So I'm going to go ahead and do that right now. 10x. This y would be subtracted to the other side. And then I would divide by whatever the coefficients are here and here. So we have x plus 3. So dy dx, you see right now I just skipped a lot of algebraic work by knowing how these separate and what I'm going to end up dividing by at the very end. Okay. So evaluate the derivative now at 2 and 6. So the difference now is that I'm not just going to use 2 the way you've been doing up to this point. Because you don't have your derivative function written in terms of only x anymore. You have it now written in terms of x, and you also have it written in terms of y. That's what this came from right here. So plugging in the 2, I would get 20 minus 6 over 2 plus 3. Okay? So that you'd get dy dx at that point, or the slope at that point, would equal to 14 over 5. Okay, so 14 over 5 would be the slope. So write the equation of the tangent line. We know that's y minus y1 equals the slope times x minus x1. This point that we already have, we have 2 is my x value. We have 6 is my y value. And now the slope that we found was 14/5. So we're going to say y minus 6 equals 14/5. And it's going to be x minus 2. You can leave it like that, or if you want to go ahead and distribute and put it in y-intercept form, y equals mx plus b, you can if you want. Last but not least, if I asked you what would the normal line be, it's going to be the same thing. Y minus 6 is equal to the slope x minus 2. The only difference is that the slope is now the negative reciprocal, and that's what would be if I asked you what's the equation of the normal line.